Origins of Multitasking and Coroutines. Both these concepts and what we call concurrency came from time sharing that was needed way back when computers were first invented. Back in the day, a CPU was just a simple chip with some sequencing circuitry and a private, super-fast memory called registers. The CPU chip was supposed to be connected to another set of chips that make up the main memory for the CPU. The main memory was divided into 4 parts. The code, which are instructions that control the sequencing circuitry, were written in binary and called opcodes. Initialized memory, which are strings and constants that are ready when the program starts running. Uninitialized memory, which is blank memory that can be used by the application code to store data. The stack, which is blank memory that is used by the CPU and the application to store temporary data, like subroutine parameters and partial results. When you put data on the stack, the memory cells can be reused by each subroutine, thanks to built-in hardware operations and the stack pointer register, called the SP. And guess what? The hardware takes care of efficiently garbage collecting the data on the stack. Early CPUs didn't have a dedicated stack pointer register, so programmers had to provide one explicitly if they wanted to use recursive subroutines. Memory is a big array of cells, and pointers are array indices that let us jump to any cell in the array. We can access any cell in the array by using an index, called a pointer. Stacks are also like arrays of cells, but the index goes up or down in a specific way. Stacks don't let us jump to any cell randomly, but they can be cleaned up very efficiently by the computer. When we create new objects at runtime, we need to allocate memory for them. This memory is usually stored in a heap or on a stack. Recursion is like a loop that keeps calling itself. When we use recursion, we make copies of variables, like parameters, and store them in new memory locations. These copies are like little stacks that prevent previous values from being overwritten. The computer takes care of cleaning up these copies when we're done using them. But here's the thing. We learned that closures, which are like functions that can remember things, need to be stored in a heap instead of a stack. This way, they can live longer and be passed around as regular functions. Lisp 1.5 is a stack-based engine. McCarthy used a heap-based garbage collector called Mark and Sweep, but Justine Tunney recently showed that this is a bit of a hassle. Since all memory cells are allocated in a strict stack-like way, we can simplify garbage collection. Due to budget constraints, we had to run multiple applications on a single CPU. We loaded as many apps as memory could hold into memory at once. We divided the code memory to fit the apps, along with some shared operating system code and libraries. The operating system created in-memory data structures for each app. These data structures had enough info to save temporary results, like register contents, along with the corresponding stack pointers and program counters. To put a process on hold, the operating system copied all the important registers and data into the process descriptor data structure for the currently running process. To switch to another process, the operating system copied all the saved register data from the process descriptor data structure into the actual registers of the CPU. Then, the actual CPU PC register was set to the saved PC, and a goto was effectively performed to resume running the chosen process. We took extra care to make sure that registers were copied in the right order and that no registers were overwritten by code from the operating system itself. We needed extra code to handle the edge case for startup. The next process runs using its own slices of memory, code, initialized, uninitialized, stack, until it decides to yield back to the operating system. This process, yield, swap out, swap in, resume running, is called context switching. The operating system sets a hardware timer to limit the amount of time each process can run. When the timer runs out, the operating system wakes up and performs a context switch, forcing the currently running process to give up to another process, usually in a round-robin manner, to give each process equal time. Adding features like tracking privileges for processes makes the operating system more complex. In the case of priorities, the dispatcher decides which process to run next. This increases the chances of bugs in the operating system. In a well-designed system, priorities are rarely needed. A famous operating system bug happened when the Mars Pathfinder landed on Mars, about 120 million miles away, and its software crashed. The bug was traced to a problem in the Wind River system's VxWorks operating system, caused by the use of priorities. To avoid that kind of bug, a technique called priority inheritance was invented. The bug probably wouldn't have happened if the Pathfinder had used multiple CPUs instead of time-sharing a single CPU. By the way, coroutines don't actually coroutine with each other. They coroutine with the operating system dispatcher function. Imagine a bunch of apps running on your computer, each vying for the same memory space. If one app goes overboard and uses too much memory, it could crash the others. To prevent this, developers added special code called bounds checking to the compiled code of each app. This code would catch any memory violations and cause an error. But it wasn't enough. The original idea had a flaw. Each app had to be compiled to a specific location in memory. If an app wanted to access a particular cell, it needed to know the exact address of that cell. This was a hassle, and it made it difficult for developers to make changes to the apps. So, developers came up with a different solution by punting work to the hardware. They added more circuitry to the CPU called memory management units, MMUs. The MMUs could slice memory into smaller chunks called pages. These pages could be scattered throughout real memory, but they would appear contiguous to an application. The MMUs would map each CPU address to a different address in real memory. This new system made it easier for developers to compile apps to the same address. An app could access memory or use jump opcodes regardless of the final real address in memory, as long as the hardware remapped every address to the chosen location in real memory. This reduced the amount of work needed to be performed by the compilers, while increasing the amount of work performed by the hardware circuits. But there was one more catch. This new system added more code to the operating system. Every time an app switched contexts, the MMU had to reload the page registers using values stored in process descriptors. This was a bit of a hassle, but it was necessary to keep the system running smoothly. With the paging scheme, based on hardware MMUs and page registers, it became possible to leave some pages on disk. This was a much cheaper storage option. Hardware circuits would map CPU addresses to real addresses by accessing the MMU page registers. If the circuit detected that a page wasn't in real memory, e.g. by checking a bit in the page register, the hardware would wake up the operating system to load the page from disk into memory. The loading process might need to free up sections of main memory by copying memory cell contents to disk, so the cells could be overwritten by new data. This increased the amount of code in the operating system. Hardware MMUs and extra software in the operating system allow you to swap entire processes out to disk and bring in other processes from disk. This combination lets you run many applications, each thinking it can use most of the computer's memory. When you add enough main memory, RAM, to a computer, several applications can live in main memory without needing to make room for others by being swapped out to disk.